All right, welcome back to the Spot on Weather. We're talking about winter conundrums, and we left off here at Arctic oscillation. This is part 2 of the video. Overall for Arctic oscillation. So now we're shifting our focus from the Pacific teleconnections now to more of the Arctic area, and then we'll move our way into the Atlantic area, the Atlantic Ocean teleconnections. All right, so for the AO or Arctic oscillation, this refers to an atmospheric circulation pattern over the middle to high latitudes of the northern hemisphere. And there's generally two phases associated with the AO. It's the positive and the negative phases, with the positive phase being characterized by lower than average air pressure over the Arctic. So you got lower pressure in the Arctic, higher latitudes, with higher than average pressure now over the northern Pacific and Atlantic Oceans. For a negative phase AO, it's characterized by the opposite. Now we have higher than average air pressure over the Arctic, paired with lower than average pressure over the northern Pacific and Atlantic Oceans. So it's a flip-flop between positive versus negative, and where these pressure differences are located. With a negative phase on the left, you'll notice how the setup of the higher pressure over high latitudes with the negative phase and the lower pressure over the northern oceans, the North Pacific and North Atlantic, that generally results in this type of jet stream configuration on the left, where you get this huge upper level ridge into the Gulf of Alaska and over parts of the western U.S., and you get this very deep trough that forms generally from the Midwest towards the East Coast with a negative AO phase. And within that trough pattern, you generally get much colder, below normal weather, winter weather temperatures. For the jet stream there with the upper level ridge there over the Gulf of Alaska into the western U.S., that's associated with much above normal winter temperatures. With the positive phase, look at our jet stream configuration, that white thick line representing the jet stream. Now we have more of a highly zonal west to east jet stream with a positive phase AO, with lower pressure now over the far high northern latitudes and high pressure over the Pacific and the Atlantic Oceans. So again, much different scenario in how the jet stream is configured. With the NAO, we're now going to focus over to the North Atlantic oscillation, the Atlantic teleconnections, and then we'll go back up to the Arctic with the discussion on the Stratospheric polar vortex, SPV. So the North Atlantic oscillation is based on the sea level pressure difference. You're looking at the pressure difference between the subtropical high, the Azores high, which is generally situated around 20 to 30 degrees north latitude in the winter, and that subpolar low, which typically sits over about 60 degrees north latitude. So you're looking at the pressure difference between those when we look at the NAO. Now the positive and negative phases of the NAO, this is important. With a positive phase NAO, this reflects below normal heights and pressure over the north central Atlantic, the eastern U.S., and western Europe. The negative phase of the NAO reflects an opposite pattern of height and pressure anomalies over these regions. Now, both phases are associated with basin-wide changes. Now, why does the NAO matter? Okay, I'll show you an example of it here in a minute. But it results in changes in the intensity and location of that North Atlantic jet stream, that configuration of how it sets up, as well as the storm track, and in large-scale modulations of the normal patterns of zonal and meridional heat transport. These phases are going to alternate in a much more amplified meridional jet stream pattern versus a more zonal west to east pattern again. And that's going to impact your heat transport mechanisms and as overall the storm track as far as your precipitation patterns in the winter season. So let's take a look. If you look at the negative mode in wintertime in the upper left of this graphic, we have a very amplified, deep trough extending from the central U.S. into the southeast coast, and then we have this huge upper level ridge in Greenland, and we get this blocking high that sets up with a negative NAO. So you get much colder and stormier conditions along the east coast of the United States when you get this negative NAO. And then look at Europe. You get much colder and drier conditions with a negative NAO across the British Isles. And then you get warmer and wetter than normal conditions across the Mediterranean countries with a negative NAO. So this thing is global in impact, not just the United States. The bottom right shows the opposite positive NAO phase in wintertime. And now we have more of an east to west, highly zonal jet stream The jet stream is strong as it blows from west to east. And generally you get more cold and more sea ice build up over the northern latitudes with a positive NAO. The coldest air remains well to the north over the high latitudes, and it's mild across a majority of the United States with a positive NAO. And then even in Europe, now in the British Isles, with a positive NAO, we have warmer and wetter conditions with an active storm track. And those same locations that were warm and wet in a negative NAO are now cool and dry across the Mediterranean in a positive mode of NAO. So big difference in the jet stream configuration again and the overall upper level atmospheric circulation. Now we're going to move into a really good discussion on the stratospheric polar vortex, SPV. Now, the polar vortex has gained a lot of notoriety over the last, I'd say, 5 to 6 winters, where you may have seen headlines or heard it on the news. The polar vortex is collapsing. That can mean significantly colder weather is going to be moving into the United States or parts of Europe. The stratospheric polar vortex, what is it exactly? It's a band of strong westerly winds that forms in the stratosphere between 10 and 30 miles above the North Pole. And it forms every wintertime. That's normal. The winds around this vortex enclose a large pool of extremely cold air. Now, when the polar vortex is strong and stable, the jet stream stays farther north, has fewer kinks in it. The cold air is contained and remains well to the north over the Arctic region, and the mid-latitudes are warmer or fairly mild. That's a stronger polar vortex, stable, and remains up over the North Polar area. Now, if that polar vortex dramatically weakens, which we've seen an increased frequency of this recently, the vortex can be pushed off the pole when it weakens, or it can even split into these lobes, into multiple pieces, 2 to 3 pieces. Now, the polar jet stream then there's going to be a response. It becomes weaker, and as that polar front jet stream becomes weaker, it becomes more wavier or more meridional. So we have larger exchanges of heat and cold temperatures between the low and high latitudes when this vortex weakens and this jet stream takes on that type of meridional configuration. And so at the surface, you get cold air that's pushed southward from the Arctic. You get all the way down to the mid latitudes, and then you get this warm air that's drawn up into the Arctic areas. So this is a case of if the Arctic is warming, specifically the stratosphere, we call it stratospheric, sudden stratospheric warming events, that tends to lead to the jet stream becoming more amplified, and we get much colder Arctic air to flow south, like we did last year in Texas this past winter in February, where Texas got hit with really, really abnormally cold weather. Now, the AO is often positive. We talked about the Arctic Oscillation. That's often positive with a stronger, stable polar vortex, by the way. So when the strong atmospheric waves, what causes this whole vortex to get displaced off the poles is when these strong atmospheric waves in that tropospheric layer, that layer closest to the Earth's surface where we experience all our weather, where we live, we're at the bottom of the troposphere where we live. When those strong atmospheric waves in the troposphere break upward into the stratosphere, the polar vortex is occasionally knocked off the pole. The vortex slows, it wobbles, it slides off the pole, and it can split into several lobes or even temporarily reverse direction, resulting in a spike in the polar stratospheric temperatures, which is called that sudden stratospheric warming, the SSW. Following the stratospheric warming event, where you get these abnormally warm temperatures up in the second layer of the atmosphere, the stratosphere, the polar jet stream then develops a more wavier meridional configuration with highly amplified troughs and ridges extending into the mid-latitudes, and they can become stationary for days. Now, under the ridges, you typically get that warm air that floods north into the higher latitudes, into the Arctic, while the polar air fills the low-pressure troughs, with the Arctic Oscillation then flipping over into a negative phase. Here's a couple great examples, like how I just mentioned how the stratospheric polar vortex seems to be getting weakened more frequently in recent winters. And in fact, there's been research just recently conducted. I just read it a couple days ago by Dr. Judah Cohen And then he also has another colleague there that worked for him at Atmospheric Environmental Research. But it's a really good article. I can reference you that in a social media post, and you guys can check it out. But with the stratospheric polar vortex, an example on the left is the February 15th to 22nd, 2021 extreme cold in the south central U.S. From Kansas all the way down into the state of Texas. We heard a lot in the news about Texas and how abnormally cold things were by that blue shading there. We're talking about temperatures on the order of 30 to 40 degrees Fahrenheit below normal in Texas during this episode, where the stratospheric polar vortex collapsed. And you look at the orange shading in that graphic on the left over the North Pole. Look how above normal those temperatures are above the North Pole as well as parts of Greenland, and how much cooler than normal it is, colder than normal it is in the United States. And this is called the warm Arctic cold continent concept, where the Arctic gets exceptionally warm, the lower latitudes tend to get much colder. Another graphic on the right there shows the this was the polar vortex collapse of 2019. This runs from January 26th to February 1st, 2019. Look at these wind chill values associated as this polar vortex collapsed from the Arctic all the way down through Canada into the upper Midwest. We're talking wind chill values in that pink shading of negative 50 to negative 60 degrees Fahrenheit. Just absurd wind chill values. So this is occurring more frequently, and there is possibly a tie-in with global warming that researchers have looked at. With global warming, the Arctic areas are warming twice as fast as the rest of the planet. And when you warm an area that's normally cold twice as quickly, there's usually going to be some form of consequence or some form of reaction by the atmosphere. Here's an example of the disruption of the stratospheric polar vortex in early of January 2021. This preceded the deep freeze there in Texas in February. So these stratospheric polar vortex disruptions actually typically occur 30 to 40 days in advance of the sensible weather being impacted is what I'm getting at. And so this example here, Amy Butler, she's the one who looked at this closely and showing you the purplish shading, the magenta shading here is the polar vortex itself. So you can see the graphic on the left there shows December 26, 2020. You can see how the polar vortex is starting to become displaced off the polar areas. It's fairly, looks like at this time it's being stretched or elongated. The middle image of January 5th, 2021 shows definitely elongation of the polar vortex as it's displaced off the polar areas. It was also the first day of sudden stratospheric warming on January 5th there in that middle graphic. And then on January 15th, we have two lobes of the polar vortex that have been displaced. The polar vortex is split into two main vortexes or vortices in general. So you kind of see how the progression occurred from December, late December through mid-January. And then after it split, it sent one of the lobes in much very cold below normal air all the way down into the central U.S., especially into Texas, where there was a state of emergency because of how cold it got. When you had snow in Houston, Texas, that's just unbelievable. In Houston has snow. So the Arctic is really starting, to really impact our weather. These polar vortex splits or elongations of polar vortex really makes a difference for our sensible weather in the United States during the winter season. The research by Dr. Cohen also showed that elongations of the polar vortex tend to lead to more of a significant cold weather impact in the eastern U.S. for the elongations, and the actual splits tend to favor the coldest air shifting into Europe and parts of Siberia. So again, it's really impressive. Now, these images are courtesy of Laura Siasto of the NOAA Climate Prediction Center, by the way. So again, recent research with the polar vortex indicates that global warming will lead to a weakened vortex, more frequent outbreaks each winter of very cold air from the Arctic into the mid-latitudes during the winter season. And you wouldn't think this, right? Intuitively, you're thinking, okay, global warming, I'm thinking the whole planet is warming up, right? And that should lead to milder winters. And so there is some research that suggests that with a weakening stratospheric polar vortex, we could actually see more frequent outbreaks of very cold air that's normally bottled up in the Arctic into the United States and parts of Europe as well. Now, when the stratospheric polar vortex is elongated off the pole, the research has shown that eastern North America bears the brunt of the coldest air when it's elongated, with a direct connection, that should be direct connection, to the Arctic. When the stratospheric polar vortex SPV is split into multiple lobes, the brunt of the coldest air occurs in Europe and then parts of Siberia. But again, this is highly dependent on how the positioning and the strength of those lobes. How does once you split the polar vortex, where those lobes go is going to be highly important as far as the sensible weather, including the temperature departures from normal, that colder weather. Again, Dr. Judah Cohen is a great resource on the SPV. You just search his name, Google his name, and you're going to find some great articles, great research done, National Science Foundation sponsored articles. So, please feel free to take a look at that if you're more interested in learning about this interesting phenomenon in the Arctic, the polar vortex. Overall, Arctic warming, I don't even have to say this very much, but I'm going to re-emphasize it anyway. Arctic warming is occurring twice as fast as the rest of the globe is seeing warming. And this results in what's known as weather whiplash, where you're getting this Arctic amplification. The Arctic level temperatures are moving toward middle latitudes more frequently during winter in association with those weakening polar vortices. This is going to produce weather extremes. You're going to see more intense weather episodes. In addition, that jet stream configuration is going to become more amplified. It's going to weaken and become more amplified. So it's very possible we'll see deeper troughs more frequently into the lower latitudes during the winter season, and more highly amplified ridges sending anomalously warm air into higher latitudes if this continues. I also want to take a look at solar activity. Just showing you this graph shows the predicted sunspot cycle flux. It's usually these ranges of sunspot activity where you get max sunspots generally occurs on the order of 11 years. It's a naturally occurring cycle of increased and decreased solar activity from the sun. Showing the years from 1913 all the way up to the present time. There is some projections in the future in solar cycle 25 as well. Generally showing a peak in the solar activity expected 2023 to 2024. We're expecting an increase in solar activity, increased number of sunspots. Generally, we are still sitting in a lull in solar activity, low solar activity, and some research has actually indicated an increasing frequency of this high latitude blocking over the oceans, the northern oceans, during lower periods of solar activity. And that tends to lead to more stagnant weather patterns and also a much greater meridional jet stream, a much more greater exchange of cold to warm temperatures and warm to cold temperatures from the low to the high latitudes, and more intense storm systems as well. When you get this meridional big dips in the jet stream, these troughs, you tend to lead to greater temperature contrast, increased energy, and increased jet stream flow, which leads to more increased upper level dynamics. But just wanted to show you solar activity and the fact that research still does indicate that we get higher frequency of high latitude blocking, which would be associated more with a negative NAO. Looking at Earth overall, general natural temperature variability over the years, I circled the main areas there, how Earth, it varies, from year to year, from warmer periods to cooler periods, and that's part of the natural cycle. But then you look at the right-hand portion of the diagram, and you'll see how now we're just kind of trending more positive, in the positive direction. These are temperature anomalies in degrees Fahrenheit, and you notice, especially since the year 2000, how things have really trended upward in the Earth's temperature anomalies overall, as compared to the circled area on the left, which was ranging from 1910 to 1960, how we had more ups and downs. So it appears that the cycle is more natural earlier on when we look at 1910 to 1960 as compared to 2000 to 2020, where it just seems like the trend of Earth's temperatures is going up. And so, it's very important to look at stuff like this and watch these trends closely. Here's some past winter variability showing the very cold winter in 2013-14, where we had a they call it the resiliently ridiculous ridge, triple R, set up over the west coast of the United States. I was out in San Diego at the time, and yeah, I mean, they had a major drought going on because of the ridge and how it just stagnated over the west coast of the U.S. Meanwhile, you had this very deep trough that set up for long periods of time during the winter of 2013-14, which directed much colder air into the Midwest and Eastern U.S. in that winter. In fact, in the winter of 2013-14, Chicago had its coldest December to March on record since 1872. Detroit had its snowiest winter on record since 1880. So that's saying something in locations that normally get cold and snowier winters. The graphic on the right is the complete opposite. The winter of, if we look at December 2018 through February 2019, look at the maroon shading indicating well above normal temperatures extending from Texas, Florida, southeastern U.S., up through Tennessee to the mid-Atlantic, Ohio River. And then we have the blue shading much colder than normal temperatures back towards the northern plains, the Dakotas, into Montana, and into western Canada. So with global warming continuing, with these temperatures of Earth increasing for this right here, showing the proof, we can expect to see wider and more frequent variability in temperatures and storm activity and precipitation from winter to winter. We'll see more frequent and extreme swings in temperature as we continue to warm the planet. This is going to become more commonplace, and I just wanted to show you a comparison between a very cold winter. I was mainly going back to 2010. When I saved these graphics, I wanted to just show you over the last 10 years or decade, how we're swinging from very cold winters on the left to very warm winters in the east on the right. And so we can expect this variability to continue. Here's another example now on the global scale on the left. Look at the winter. This was, again, that winter of 2019 into 20. I mean, yeah, we were warm in the eastern U.S. that winter, but look at the whole globe. Look at parts of Europe. Look at parts of Siberia on the left. The winter of 2019-20, just incredible over Siberia, over parts of northern Europe. Countries that expect much colder winters, well above normal in that particular winter, on the range of 3 to 5 degrees Celsius above normal. I mean, we're not just talking about a degree Celsius above normal. We're talking pretty extreme ranges. Look at the planet as a whole. The blue shadings indicate below normal temperatures for that winter, but overall, look at the entire planet just warmer than normal. If you look at the graphic on the right, I'm showing you the overall 500 millibar geopotential height anomaly at 18,000 feet, the upper level heights. Look at the winter, that particular winter. This was 2013-14 winter, and I think, let's see, yeah. So that was the one I showed you here on the left. But look at the upper level pattern. That dashed black line in the graphic on the right is the actual polar front jet stream, and the purple shading is just extremely cold temperatures over, situated just south of Hudson Bay, directing much colder air into the upper plain states, Midwest, into the East Coast. Just incredible. And then the orange shading on the right graphic shows where those upper level ridges, anomalously high upper level heights were setting up over the oceans. And so with global warming, again, expect wider and more frequent variability between winter to winter. With the jet stream pattern overall, I just wanted to show you more of a global scale on the left, just how incredible that is. Right, I want to turn the attention now to constructive versus destructive feedback. At times, these teleconnections, which we've talked about in this video, they work together in one direction in an amplifying manner, and this is known as constructive feedback. So, for example, if I combine a negative NAO and a negative AO and a positive PNA pattern, that is going to result in a constructive feedback situation with much colder temperatures across the eastern U.S. and much warmer temperatures, well above normal temperatures across the western U.S. But it's at other times where these teleconnections, they work actually against each other in opposite directions, and this is known as destructive feedback. An example of this would be a negative NAO and a negative PNA pattern. So the negative NAO is telling me I should have a high latitude block in the North Atlantic Ocean. I should have a deep trough in the eastern U.S. I should have a a colder and stormier period of time of weather there across the eastern U.S. But that negative PNA is indicating otherwise. It's saying I should have a upper level ridge and dry and warmer than normal temperatures across the eastern U.S. So that's a destructive feedback situation where one teleconnection is saying one thing and the other teleconnection is saying the opposite thing. And so the trick in all this is determining the teleconnection, which one is stronger in magnitude, which one is going to be more dominant. So some of the most extreme winters, we see exceptionally warm or cold temperatures in one direction. These have been associated during constructive feedback situations where the teleconnections all are lining up and working together in one direction, whether it be a warmer or colder winter scenario. Certain teleconnections can also be stronger and more dominant over others during the winter season. So for example, I can have a very strong El Nino, or I can have a EPO which favors a more zonal, highly amplified Pacific jet, but I also can have a negative NAO at the same time. And so, or a negative AO. And so, which of these teleconnections is strongest and most dominant? And that's the real challenge in seasonal forecasting. Just because a teleconnection is supposed to produce certain weather, that's not always the case. And I mentioned this earlier in the video in part 1 where I said a couple of winters ago there was El Nino, but it never behaved like El Nino for the eastern U.S. El Ninos, for example, in the mid-Atlantic states are typically cooler and wetter than normal. Well, we were drier and warmer than normal for most of that winter. And so just because, the forecast is for a La Nina coming up this winter, which is true, I believe there's a 70% chance of a La Nina, it doesn't mean that conditions are going to behave identical to what you would expect for a La Nina because they are never exactly alike. As far as these closing notes for today's video, forecasting the weather for the winter season is extremely challenging, and it remains an inexact science due to so many winter variables on a warming planet on top of that. We looked at all these things that go into winter weather, could really impact the winter weather across the United States. There's countless numbers of climatic drivers. Okay? The atmosphere-ocean interaction, extremely dynamic. I've sailed on many of the oceans from the Pacific to the Atlantic. I've been in the Mediterranean, been in the Indian Ocean, and it was always fascinating to watch how the atmosphere and ocean interact. From the simplest wind motion over the waters, stirring up wind waves, to distant storms, and how that energy of distant storms translates to the ocean surface in the form of swell waves or longer period waves. The atmosphere-ocean interaction is just huge across the Pacific Ocean, especially as far as our bearing on our winter weather in the United States each year. I wanted to show this. I have a couple more slides I'm going to show as kind of extra bonus. I grew up in the Midwest, and I tell you, one of my favorite times of the year in the Midwest was the fall, was autumn. Especially the harvest moon. The harvest moon is the full moon closest to the autumnal equinox, to the first day of fall. And there's something about this picture that's just so mesmerizing for me. And it may be mesmerizing for you if you're from an area that's more in the country away from big cities. But this is just a great example. We got some barns in this picture. We got that huge full harvest moon. It just brings back a lot of great memories. Okay, I'm going to go out of this for a minute, and I just want to end tonight, or today's video. I'm going to talk about this real quick. The Earth goes through natural ups and downs in its temperatures. Back in the 1970s, I got these covers of these magazines that I put in this on the slide, just to show you what people were talking about back in the 1970s. Time magazine covers, How to Survive the Coming Ice Age in 1973 on the left. The big freeze, 1973 there, as you go from left to right. Then you got the cooling of America, 1979. And then you get the big freeze. Look at this guy. You know, he's got a ski mask on. Look at all the snow and stuff on that ski mask. So the 1970s were a very cold period of weather for the United States. And then what happened over time is we get this. You know, we're getting headlines. I didn't collect the headlines like I did with the 1970s headlines in the previous thing I just showed you. But look at the globe there on the bottom, in this graphic on the left, just is real startling. If you look at the temperature anomalies, degrees Fahrenheit, 1981 to 90 on the left. Okay, so we were still a fairly cool planet by the blue shadings, right? Over a lot of part of the northern hemisphere I'm showing there. But then look at 2011 to 2020 on the right. And look how much warmer than normal those temperatures are. Yeah, so big changes, and I'm not really going to delve into the anthropogenic versus natural climate variation discussion here, but I just wanted to show you how things are changing. And with this global warming, we're going to disturb the climate system. We're going to disturb the natural occurrences of the seasons more and more with each passing year, the more we warm the planet. And again, like I talked about the polar vortex and talked about Dr. Judah Cohen's research. Look at the image on the right there. Article that was done in the WeatherWise magazine. Where have all the winters gone? You know, this is showing you I believe it's a 1967 blizzard. That might be the 67. Yeah, it's a 1967 blizzard in Chicago where they end up getting 23 inches of snow. And look at all these cars just stuck in snowbanks, right? It's interesting to watch, and I'm very intrigued on seasonal forecasting. That's what I really enjoy to do. But how the Earth is changing is really startling. The temperatures and all these natural variations. What happens is when you overheat the atmosphere and the globe, there's going to be a response. Whether that's a breakdown in the ocean circulations, which has been discussed recently about the Gulf Stream circulation. I cover the ocean and the weather video about the thermal haline circulation with the salt and temperature differences, or other things. So there's going to be impacts. Nature is going to create, the atmosphere is going to create different ways to deal with this overheating concept. All right, that wraps things up on the video, part 2. I hope you enjoyed this winter weather, winter season conundrums. There's a lot that goes into the seasonal forecasting. And I can't wait to share what our thoughts are on the winter weather forecast coming up here next month in October. Can't wait for that, and we'll be doing some in-depth analysis on the winter weather forecast, and we'll be showing those areas of below normal and above normal temps, below normal and above normal precip. We thank you so much for subscribing to our channel. I am very passionate about the weather, and I just really enjoy sharing this information with you, and really hope it intrigues you into doing further research yourself and to really wanting to know more about the wonderful planet we lived on called Earth. All right, that wraps things up. It's Spot on Weather, where we do accuracy through precision. Check us out on social media, Facebook, Twitter. Check out the Spot on Weather Weebly website for the latest forecasts, as well as blogs, weather photo gallery, and so much more. Definitely got to check it out. All right. Thank you so much for watching and subscribing. Take care and have a blessed Labor Day weekend, everybody.